Okay, so we continue to work through the review problems for the final exam. We're doing, going to write up the solution here for number 7, which is, the question says a 50-gram ice cube can slide without friction up and down a 30-degree slope. The ice cube is pressed against the spring at the bottom of the slope, compressing the spring 10 centimeters. The spring constant is 25 Newton per meter. And then part A, when the cube is released, what total distance will it travel up the slope before reversing its direction? All right, so that's a lot of information. Let's try and break that down. So we have a slope. We can get that in here. And it's 30 degrees. And we have a block that's down at the bottom. And it has compressed a spring down here. So maybe normally the spring is this long, right? And the block sat on it and compressed it. And so this distance here is 10 centimeters or 0.1 meters. So I'm going to put that here on my list of things I know. The amount that the spring is compressed is 0.1 meters. Okay. And then, so it's going to be released. It's going to start moving, right? So it's going to get here and be moving at some velocity, and then it's going to slide up some distance where its velocity will be 0, and then it will turn around and come back down. So this is what we need to try and figure out, right? So how far up the incline is it going to go? This distance. So let's say, so now I'm going to just define my coordinate system, right? So let's say x, we can put here, put our origin here. So this is our x direction, and here's our y direction. So if we're thinking about this in terms of energy, then you know the block is going to have potential energy at these different points, and so here we'll call this our initial height, and here's our final height. Okay, so we can list a few other things that we know. That the mass of the block is 50 grams, 1, 2, 3, so 0.05 kilograms. And theta is 30 degrees, and the spring constant K is 25 newtons per meter. So that's what we know. Okay, so then for part A, we want to find x final, which would be this distance up here. Okay, so it says it's ice and there's no friction, so we can use conservation of energy here, especially with the spring and the sliding and all these different things going on. So let's think about what our energy is initially, right? So here, the different kinds of energy that we could have, right? So we have spring potential energy, we have kinetic energy, and we have gravitational potential energy. And if I just do a quick bar chart, what that looks like, right? I have some spring potential energy initially, and I have some gravitational potential energy, but I have no kinetic energy. And then at the end, I'm going to have no kinetic energy as well because we're stopping it at rest. We have no spring potential energy. That's all used up. And we're going to have more, I guess I got to go up this high, something like that, for gravitational potential. Okay, so this is our conservation of energy equation. So we have energy in the spring initially, plus the gravitational potential energy initially, plus the kinetic energy initial is going to be potential in the spring final, plus gravitational potential final, plus kinetic final. And then right away we want to cross out things that we know are 0, just to make our lives easier. So we said kinetic energy at the end will be 0, and the spring energy will be 0, and kinetic energy initially is 0 as well. Okay, so then we'll just continue with the terms that are non-zero. So 1/2 K delta X spring squared plus mg h initial. This is what we have initially, and at the end we're going to have mg h final. Okay. So if we can figure out the difference between y final or h final, whatever I called it, and y initial, right? This is our delta h. Then we can use trig to figure out what the length is along the incline. So that's a common translation we need to do. Okay, so we want to find H final minus H initial. So let's bring this over to the other side. So we have 1/2 K delta X spring squared is mg H final minus mg H initial, which if I factor out my mg, I get mg times H final minus H initial. This is what we want to try and solve for. So I'm going to divide both sides by mg, and then just swap things around. So I have my unknown on the left, so I have H final minus H initial is K delta X spring squared over 2 mg. Okay, so we know everything now. And then we can just plug in for our values, right? So K is 25 newtons per meter. Delta X spring is 0.1 meters squared. And then we're going to divide by 2. And the mass is 0.05 kilograms. And G is 9.8 meters per second squared. All right, so you guys calculate, and I will calculate, and let's see what we get. So 25 times 0.1 squared. Okay, divided by 2, divided by 0.05, divided by 9.8. So I get 0.255 meters. Okay, hopefully that's what you guys got as well. Okay, and now we want to relate that to the distance traveled along the incline. So again, this is theta in here, so we can use our trig functions to show that sine theta, I'll put it up here, sine theta equals H final minus H initial over X final minus X initial. Okay, so if we want to solve for this, it tells me that X final minus X initial is H final minus H initial divided by sine theta. Theta is 30 degrees, so it's good to know sine 30 degrees is 1/2. So it means that I want to double my distance here. So I'm going to do 0.255 meters divided by 1/2 is 0.51. Yay. Okay, so part B is a little more complicated. Part B is going to add friction. So the ice cube gets replaced, and we have a plastic cube, and we have kinetic friction, mu k equal to 0.20. And then we need to know, same thing, how far up the slope is it going to go before it stops. So if I think about what the difference is of adding friction, the simplest way to think about it is that it's not going to go up as high. So let's just look at it in terms of the energy bar charts here. So if we do it the same way, we have potential in the spring, potential of gravity, and we have kinetic, right? All these initial values. Sorry, that's a G. And then that will equal to the energy of the spring after, at the end, the gravitational potential final, the kinetic final. And then we have this extra term that's kind of the way that we try to deal with friction right now is to say that work was done. So friction took some energy out of our system. So that's the work from friction. So we don't know exactly how it's going to balance out, right? But if we just kind of sketch things again as we did in the first part, we'll say that's what our energy is to start with. We don't have any spring. We're going to gain some gravitational potential energy, but we're going to lose some to work. So, maybe my potential energy looks something like that. I don't really know how these are going to break down, but I'm just kind of sketching so I know conceptually what goes into my conservation of energy equation. And then we can fill things in, right? So we have initial spring energy, initial gravitational potential energy. We'll just put all these terms in and cross them out in a second. UG final plus K final plus the work done by friction. Okay, so it starts at rest, so kinetic is, initial is 0, it ends at rest, final kinetic is 0. It does have spring energy and potential. Initially it has no spring energy at the end. So very similar, except that we have this issue, right? So, and the work done by friction is the force of friction times x final minus x initial. Okay, and this is what we want to find, right? Okay, so how are we going to do that? I'm going to change pages here, and we'll look at what the forces are acting on the block as it goes up the incline, right? Because now we have a plastic cube that's sliding. So we're going to just draw our free body diagram. So we have the force of gravity going downward. We have the normal, which always comes up perpendicular to the surface. We'll look something like that. And then if the object's moving in this direction, if that's our velocity, friction will oppose that. So friction looks like that. So we need to know what this force is in order to calculate the energy lost by friction. So we know friction is mu times the normal. And in order to figure out what the normal is, we need to sum our forces in the y direction. So here's x, here's y. So let's do our sum of the forces in the y direction equals MAY. The block is not accelerating in the y direction, so that's 0. So we have the normal minus the y component of gravity equals 0. And again, if we just want to look at our geometry here, so this is theta. This angle in here is 90 minus theta. So if I think of breaking my gravity into a component down the plane and one into the plane, this angle in here is theta. So it means that my y component is the adjacent side. So that's the normal minus mg cosine theta. Cosine is the adjacent side. Equals 0. So my normal equals mg cosine theta. Okay. So now I can go back to my conservation of energy equation. So I had, I'll put that up here so you guys can see that. Okay. So I'm just going to continue down here. So I have my spring energy is 1/2 k delta x spring squared plus mgh initial equals mgh final plus the force of friction times x final minus x initial. Okay. So remember that we talked about how h final minus h initial is related to x final minus x initial. But let's bring this term over. So on the left, we're just going to be temporarily left with the spring energy. So we have mg h final minus mg h initial plus the force of friction x final minus x initial. Okay, so I'm going to factor out my mg here, h final minus h initial. And we had, from the beginning of the first page, the connection between these two. Okay, and this is what we want to solve for. So I'm going to replace this with it's x final minus x initial times sine theta. And then the force of friction I can break up as mu times the normal, which is mg cos theta. And we have x final minus x initial equals 1/2 k delta x spring squared. So now this is what we want to solve for, how far up the incline is going to travel, so we'll factor that out. So we have x final minus x initial, and then left inside here we have mg sine theta plus mu mg cos theta. So that looks nice. Don't you love algebra first? And then we can divide here by mg sine theta plus mu mg cos theta And I'm going to flip my side, so I have x final minus x initial is k delta x spring squared over 2, and then I'm just going to factor out mg just so I don't have to plug it in multiple times to my calculator. So 2mg, and then inside the parentheses we'll have a sine theta from the first term and a mu cosine theta from the second term. Okay, so let's plug in. So we get k is, I'll probably go down because I always end up running out of room, so we get 25 newtons per meter. Delta x spring is 0.1 meters squared. We have 2 times the mass, 0.05 kilograms, times the acceleration of gravity, 9.8 meters per second squared, and then sine 30 degrees plus mu, which was 0.2, cosine 30 degrees. Okay, so we'll plug all that into our calculator. And we get something like 0.38 meters. Okay, not so bad.